Okay, welcome to the video on impact force. We're going to take a look at how to measure the amount of force occurring when two particles impact each other. And this is not going to be a fully accurate scientific method. It's just an approximation that works pretty well. Because really we just kind of need a consistent model that works in TP so that we can detect, hey, if there's enough force in that collision, then we can either have dust fall off these particles or we can have them volume break or whatever. But the way that we're going to do this is we're going to have a large particle here go in this direction, and then we're going to have a smaller particle go in this direction, and obviously they're going head on. So head on, there's going to be more force or more impact force involved than if we have one going this way and the other going in the same direction. It's kind of like getting bumped in the back of a car as opposed to getting involved in a head-on collision. So the head-on collision is going to have more force involved. So what we're going to do is we're actually going to take the mass of these particles multiplied by their speed. So the mass times speed of that particle. And then what we're going to do is we're going to add this with this one, but we're going to take the direction into account on this second particle. And what we're going to do is we're going to take the dot product of those two vectors. So if the dot product of two vectors who are opposite or opposing each other, that dot product is equal to -1. And then if two vectors that are the same, that dot product is going to be 1. And then if they're perpendicular, that dot product is 0. Now you think about it, going opposite or head on, that should have a lot more force than something going in the same direction. So what we're going to do is we're actually going to multiply our dot product by -1. So we're going to have dot times -1, and then we're going to multiply that against that second one. And we'll see how this works here in just a sec. Okay, so we've got here is our sphere 01, which is this big guy. It's got a radius of 20, so a total diameter of 40. And you remember that, here's the mass, and we've got mass is 1, and size mass is checked. And so with the diameter being 40, remember that the way that TP measures size is by the longest edge of a particle. It does not take into account, volume of the particle. That would be pretty nice. And actually, a really good way to deal with that in production is to write a little Mac script that measures the volume of your particle, and then writes that as a user-defined property, whatever that value is. And then you can go ahead and use the user-defined properties script that we wrote. And you can modify that in order to be able to read these different values. And another good user-defined property that comes up when we're dealing with impact force is things like volume breaking threshold. So if we wanted to say this big particle has a VB thresh equal to 2000, and what we could use this for is saying, hey, if this particle's involved in a shape collision, has an impact, and the total amount of force is over 2000, then this particle is going to go ahead and volume break. So that's another great way to use user-defined properties. Okay, so, and remember, on the mass, when size's mass is checked, it's going to use the longest edge of the size. And this mass then actually also acts as a multiplier. So we're going to leave that at 1 for now. Okay, so back here into TP, and so this big particle, if we can, TP, yeah. So the big particle here with the radius of 40, the size of 40, it has a speed of 50 units per second. And so 40 times 50 is obviously going to be 2000. And our smaller particle has a radius of 10, so a diameter of 20, and its speed is only 2. And so 20 times 2 is going to give us a value of 40. But there's something kind of interesting and unfortunate, a little pitfall that we have to watch out for, is that you'll notice our small particle here, it starts moving, and then right around 11 or 12 frames, it stops moving. And the reason for this is because there's no friction in the scene, but on the SC operator, are the deactivation parameters. And those deactivation parameters are used during collisions with lots of objects to kind of measure, hey, how active are the particles? And if they're not very active, then go ahead and just tell them to stop, put them to rest, and then that particle stops moving. So that's what's happening to this guy, is that this deactivation time is set to 0.5, which is a time in seconds. So, and we're in frame time is film time, so 24 frames a second, so right around 11, which is 12 frames, that equals half a second. And so our velocity of this particle is below 2.5. Remember, it's only set to 2. So 2 is less than 2.5, and so our particle goes to sleep and stops moving, which is bad. So what we have to do is we actually have to lower that velocity threshold. So any particle who's involved in a shape collision, whether activate all is turned on or not, and as soon as that particle's velocity goes below 0.5 and stays below 0.5 for half a second, then that particle is going to go to sleep. Okay, so now our particle keeps moving because we lowered that threshold, and boom, it gets bumped and moves way over. So, and also on our SC, sizes mass is not checked. We do not want that. Okay, so how are we going to approach this? Let's go ahead and, well, we've got that formula that we looked at, and something critical that we need to know is that the collision particle A and B coming out of here, we cannot just grab their a particle data and say, hey, give me the velocity and give me the mass, because at this point, these outputs, the particle has already gone through the shape collision step, and it's already had its direction changed. It's already been involved in the collision. So all we see here is the result. So one important thing that we need to do is actually capture that particle direction and speed before it gets into the shape collision. So we'll just go ahead and create a new dynamic set. We'll call this store data. And store data is pretty simple. We're just going to go ahead and take our objects. We're going to use a memory. And memory, really good idea with memory, remember, is to, if you're going to be storing variables on them, to name that memory something unique, preferably something that pertains to the variables. So we're going to go ahead and store particle mass, particle speed, and direction. And we're going to go ahead and add those as inputs. And because these are explicit data types like mass and speed and direction, we can connect those directly to the particle, and it will just pull that information out of the particle itself. You do not have to expose like velocity, calculate the speed or the direction, any of that. You can just grab it right out of the particle. Okay, so every frame or every time sample, depending what our sampling is set to, our particle is going to, our tree evaluates top down, and so the particles get to this step in this rule, and then they're going to go ahead and store their data. And that's just so that every frame or every sample, that particle's data is current. That might seem like a lot of overhead, but fortunately it doesn't seem to be an issue. We were doing some pretty big structures with like 2,000 or 3,000 particles joined together, and there was not a problem. But of course it also depends on your machine speed. So, okay, but anyway, we store those values. And now we're going to get into the SC, and we want to go ahead and look at the particles after they've been involved in that shape collision. And we'll go ahead and look at their mass, speed, and direction. And we'll just duplicate that for this guy. And of course, according to our formula, we're going to go ahead and mass times speed. Multiply those. And then we're going to need to go ahead and calculate our dot product times -1. So we're going to just use, instead of using an expression operator, we've got one built already under M3D vectors called VOPs, which is useful for dealing with vector operations, whether you're adding them. But if you're going to do a dot product, we have to put in that multiply symbol, press enter to set it, and then we have to watch out because our only output is a vector, and a dot product is a scalar value, so we need to change that and just add a new output. You can have you can leave multiple outputs there, that's okay. But remember, if you do have multiple inputs on an expression operator and you're not using any of them, like if we use that direction and this direction, but we have this input here, the expression operator is going to run into problems. It's not going to work. And so make sure that you do not have any extraneous inputs. So let's remove that. Remove you. Oops, now I'm creating new ones. This is taking a step backwards. Let's remove input. Okay. So we want to take those two direction vectors, the directions they were going before they were in the shape collision. That's why we're looking them up with memory. Then we're going to get the dot product of that, and we're going to multiply that by -1. And let's go ahead and revisit our little fake physics formula, and we're gonna go ahead and add, this force value with this whole product here. So let's do that portion first. We're going to take this amount of force that we've got, the mass times the speed, and we're going to add that. But we need to go ahead and actually take our dot product multiplied by our force value of the second particle. So this is going to be a multiply. We're going to take that dot product, multiply it against the force, the mass times speed of this particle. Okay, and then we're going to go ahead and add that to this. And that's going to be our cumulative amount of force, taking into account the particle's directions, their mass, and their speed. So again, not scientific, but it will tell us enough about what's going on with the particle. Okay, so we're going to add those. Let's go ahead and get a memory in here so we can actually see. We don't need that, but we do need a input. We'll call this force. And force, we'll go ahead and expose that to debug. Okay, so you'll notice right away that we get this thing where the debug is showing us this value every time. And this is because we are just looking up these values. We need to actually control when these values are looked up or turned on. So we'll expose they're on, and we will go ahead and connect that to the collision index. That may or may not be the best output to connect that to, but it'll work. Or not. Hush my mouth. Okay, well, let's do it on this guy. Collision index. Alright, something worked. Okay, so they collide and bang. We get a value of 2040. So you remember we had 40, a size of 40 times 50 units per second velocity. And they're going head on. So this guy's force here on the left, that's about 2,000 units. The guy on the right, he's only got a diameter of 20, and I think his speed was really low. It was only 2. So 20 times 2 is 40. So you add them together, and according to our dot product, where they're going head on, would normally equal -1, but we multiply that by -1 in order to make it positive, so that it's a larger collision impact than when they're going the same direction. And let's go ahead and take a look at what happens now if we send this particle in the same direction, this particle on the right, to go in the same direction as the particle on the left. So they're going the same direction, different speeds. Okay, so we get values like 1960, negative 1960. We might need to turn that into an absolute value. Obviously, force probably couldn't be negative unless it was some kind of black hole or vacuum or something. But okay, so there's less force involved there. That's what we want. So this is a way for us to kind of hack together a method to measure that impact force. And again, I apologize, it's not the super scientific method, but it's good enough that we can actually use it to detect that threshold and then either cause some secondary reactions, cause volume breaking, etc. So, and then what you'd, yeah. Okay, well, enough of that. Let's go ahead and get going.